Single parameter domains. The unrestricted case Vi equals to R to the A basically means that the valuation space has full dimensionality. The opposite case is when the space Vi is single dimensional, i.e. there is a single real parameter that directly determines the whole vector Vi. There are several possible levels of generality in which to formalize this, and we will consider one of intermediate generality that is simple and yet suffices for most applications. In our setting, each bidder has a private scalar value for winning with losing having value of 0. This is modeled by some commonly known subset of winning alternatives, Wi, which is a subset equals to A. The main point is that all winning alternatives are equivalent to each other for player I, and similarly, all losing outcomes are equivalent to each other. All the examples in section 9.3.5 fall into this category. A simple example is an auction of one item, where Wi is the single outcome where I wins. A more complex example is the setting of buying a path in a network, subsection 9.3.5.6, where Wi is the set of all paths that contain Hi. Definition 9.33. A single parameter domain Vi is defined by a publicly known Wi, which is a subset of A, and a range of values between t to the 0 and t to the 1. Vi is the set of Vi. Capital Vi is the set of little vi, such that for some t to the 0 less than t less than equals to t to the 1, Vi of A equals to t for all A in Wi, and Vi of A equals to 0 for all A not in Wi. In such settings, we will abuse notation and use Vi as the scalar t. For this setting, it is quite easy to completely characterize incentive-compatible mechanisms. Definition 9.34. A social choice function f on a single parameter domain is called a monotone in Vi if for every V minus I and every Vi less than equals to Vi prime in R, we have that f of Vi V minus I is in Wi implies that f of Vi prime V minus I is in Wi. That is, if valuation Vi makes I win, then so will every higher valuation Vi prime, which is greater than equals to Vi. For a monotone function f for every V minus I, for which player I can both win and lose, there is always a critical value below which I loses, and above which he wins. For example, in a second prize auction, the critical value for each player is highest declared value among the other players. Definition 9.35. The critical value of a monotone social choice function f on a single parameter domain is Ci of V minus I, which is equals to the superior of Vi such that Vi is those f of Vi V minus I not in Wi. The critical value at V minus I is undefined if the set of Vi such that f of Vi V minus I is not in Wi is empty. We will call a mechanism on a single parameter domain normalized if the payment for losing is always 0, i.e. for every Vi V minus I such that f of Vi V minus I is not in Wi, we have that Pi of Vi V minus I equals to 0. It is not difficult to see that every incentive-compatible mechanism may be easily turned into a normalized one, so it suffices to characterize normalized mechanisms. Theorem 9.36. The normalized mechanism f P1, P2, P3 until Pn on a single parameter domain is incentive compatible if and only if the following conditions hold. 1. F is monotone in every Vi. 2. Every winning bid pays the critical value. Recall that losing bids pay 0. Formally, for every I, Vi, V minus I such that f of Vi, V minus I is in Wi, we have that Pi of Vi, V minus I equals to Ci of V minus I. If Ci of V minus I is undefined, we require instead that for every V minus I, there exists some value Ci such that Pi of Vi, V minus I equals to Ci. For all Vi such that f of Vi, V minus I is in Wi. Proof. If part. Fix I, V minus I, Vi. For every declaration made by I, if he wins, his utility is Vi minus Ci of V minus I, and if he loses, his utility is 0. Thus, he prefers winning if Vi is greater than Ci of V minus I, and losing if Vi is less than Ci of V minus I, which is exactly what happens when he declares the truth. Only if part first condition. If f is not monotone, then for some Vi prime greater than Vi, we have that f of Vi prime V minus I loses while f of Vi V minus I wins, and pays some amount P equals to Pi of Vi V minus I. Since a bidder with value Vi is not better off bidding Vi prime and losing, we have that Vi minus P is greater than or equals to 0. Since a bidder with value Vi prime is not better off bidding Vi and winning, we have that Vi prime minus A is less than or equals to 0, which is a contradiction. Only if part. Second condition. Assume that some winning Vi pays P greater than Ci of V minus I, then using proposition 9.27. All winning bids will make the same payment, including a winning Vi prime with Ci of V minus I less than Vi prime less than P. But such a bidder is better off losing, which he can do by bidding some value V to the lose less than C of V minus I. In the other direction, if Vi pays P less than C of C of V minus I, then a losing Vi prime with C of V minus I greater than Vi prime greater than P is better off winning and paying P, which will happen if he beats Vi. Notice that this characterization leaves ample space for non-FI maximization. For example, we can implement social functions such as maximizing the Euclidean norm, argument max of the summations of Vi of A squared, summing for all index I, and the maxima is taken among all A, or maximizing the minimum value argument max A of min I of Vi of A. Indeed, in many cases, this flexibility allows the design of a computationally efficient approximation mechanisms for problems whose exact optimization is computationally intractable. An example is given in Chapter 12.